Hello everybody, my name is Jiří Kolasa and I am working in the University of Chemistry and Technology in Prague. Just in case you wanted to find me, here is my location. And this course will be about molecular modeling and simulation. The first lecture is a popular introduction to this topic. Modeling is a very general word. We can model whatever we wish. In chemistry, we have several levels of modeling available. This course will be mostly about the so-called atomistic modeling. It means that the basic element of modeling will be atoms. You can imagine atoms as small soft balls essentially for this, but of course there is some mathematics about the method we will use. In chemistry, often we use also the Schrödinger equation. You certainly have heard about it. But this course will not be about this equation and about these methods. If we use the Schrödinger equation, we divide atoms to smaller elements, to nuclei and electrons. By solving the Schrödinger equation, we can calculate quite accurately small molecules. The bigger system, the worse accuracy. We can calculate spectra, gas phase properties. For example, for reactions in the gas phase, we can quite well predict the chemical equilibria, even in circumstances that are not available on Earth, for example, in atmospheres of stars. We can get a lot of information about chemical kinetics, about photochemistry, and so on. Okay, so these are smaller elements, important for chemistry, but not covered by this course. We can go with dividing the world into smaller and smaller elements further. So the next level is a system where we treat our molecules or the world as composed of nuclei, electrons and photons. This is described by quantum electrodynamics. This is an extremely accurate theory. It is believed that it's accurate for good system up to 15 decimal digits. We can calculate spectra of very simple systems and compare them to the experiment, and it does work. Of course, at this moment, if our elements are nuclear, we can ask whether nuclei are elementary particles or not. And it's known that nuclei are not elementary particles. They are composed of protons and neutrons are composed of quarks and gluons and so on. So this is a field of physics of elementary particles, and we have the so-called standard model, which quite well describes this world, but it is extremely demanding for calculation. For example, still, it's not easy to predict, for example, stability of nuclei accurately enough. On the other hand, in the field of chemistry, using the Schrödinger equation, we can quite well predict spectra of small molecules. Here our knowledge essentially stops as regards reduction to smaller and smaller parts. We don't know how to merge this theory of elementary particles and gravity. And for example, how to explain the so-called dark energy. This is called the grand unified theory. Certainly this course will not be about this. But okay, we started with atoms, and we can do the opposite line of modeling. Sometimes we need to describe systems which are very large. If we did this at the atomistic level, it would be very demanding for calculation. So we can use the so-called coarse-grained models. At the simplest level, we can have, for example, a polymer and one bead will be one element. It will maybe a sphere or ellipsoid or something like that. At another level, a polyatomic group of certain properties, for example, a dipole moment and so on, is described by one element. Quite a typical example are surfactants. They are composed of heads, which are attractive, and they like water, and then a hydrophobic tail. One of common force fields for these systems is a so-called compass force field, and in this force field, 4 water molecules are described by one very soft and specially interacting sphere. But if this level of coarse graining is not enough, we can go further to a more microscopic scale. We can describe dispersions or granular materials. In dispersion systems, a micelle, for example, or something, or a nanoparticle in general, is an element of modeling described by some forces and shape and so on. Granular materials, for example, sand. Maybe a question: what is the shape of the pile of sand if we drop pieces of sand from the top? One typical example, or another example from geology are landslides. If we have such a pile, so it can break and slide away, which is important if we ask where to build houses and so on. And at an even bigger level, we have a continuum. Here's a different type of modeling. Instead of any particles of different properties and sizes, we have a continuum, which is described by partial differential equations. By these methods, we usually study the heat conduction. Weather forecast is important. It is a complex model where we have mass transfer, that is wind, and heat transfer, and water precipitation, and so on, and is described by a set of complex equations, mostly partial differential equations. Another example, actually the first computer in the world, ENIAC, was used to this, is to calculate the atomic bomb by the flux of neutrons going through certain layers of uranium or plutonium. Also in civil engineering, when building bridges and houses and so on, we use statics, that is forces in a material. Again, it is solved at the level of continuum, usually by partial differential equations. Also, the general theory of relativity is a theory which is based on partial differential equations working on the space-time. So we have gravity, and we have black holes and gravitational waves and so on and so on. And we would like to merge these levels, but unfortunately now this is not known how to do. Perhaps one more note here: we can also combine several levels into something bigger. A typical example which is often quoted is if we are interested in enzymes. Enzymes are big proteins, and they have an active center. There are chemical reactions going on at this center, so we need the Schrödinger equation, quantum chemistry, to describe this active center of the enzyme. But we are able to treat at this level only the center and a small neighborhood. Otherwise, all these calculations would be inaccurate and very demanding, time-consuming. So we take this center and it is several atoms here, and we take an atomistic model of the rest of the protein and put it around. in some way. So we have a bigger system. The center is treated quantum mechanically and the rest is treated at a classical level, and there are some methods how to bind this together. But still, sometimes this is not enough. For example, this protein may be in water. In water it means if the protein is large enough, tens of thousands of water molecules. Again, this is demanding, so we can use a continuum instead of that water around. So we have a third level of modeling. So this is called multiscale modeling, and the type that combines the Schrödinger equation or quantum chemistry. In general, we have more methods in quantum chemistry than only Schrödinger equation, and atomistic modeling is usually called QMMM. It means quantum mechanics and molecular mechanics. This is this level. Of course, we can have more levels here. An important concept in modeling is the potential energy surface. Here we start with the level of nuclei plus electrons, but we realize that electrons are much faster, much lighter, about at least 1,000 times lighter for hydrogen or 10,000 times lighter if we take heavier atoms. That is, essentially, electrons move so fast that we are not interested particularly in these fast motions like in photochemistry. We can integrate out or smooth out the electronic motion. We then define the potential energy surface as potential energy, which is a function of positions of all nuclei. This is called the Born-Oppenheimer approximation. It is an approximation. We cannot study very fast processes by this method, but it is a very useful method even for chemical reactions and other phenomena. I will show you now one example of the potential energy surface. What you can see here is a dimer of water in a very simple model called SPCE model of water. I will speak about it a bit later. You can see the minimum energy here, and what we can do now, I can, for example, click this atom and move it out, so this bond will be longer. I can recalculate energy, and you can see that the energy, which is here in kilocalories per mole, much higher. I can return back by minimization, by optimization the energy, so it will minimize it again, and I can play with it further. For example, if I take this molecule as a whole and move it a bit, and again if I recalculate energy, I can see that it is higher. It is not in the minimum, but now the energy difference is much smaller because I moved a whole molecule and only I broke the hydrogen bond here. So just one example what is the potential energy surface. I can calculate it for given molecule. Approximately, it was an approximation. Another example that certainly you have heard in basic courses of physical chemistry is the use of the potential energy surface to study chemical reactions. That is, we have a lot of atoms, for example, in two molecules that react together, and we have the energy as a function of n atom that are totally 3n numbers. We can reduce it some way, but let us say there are 3n. Of course, I cannot draw such a function with 3n coordinates even for such a simple system as two water molecules. So here there is a picture of only two-dimensional potential energy surface, and you probably know that the reaction proceeds from one minimum there's some thermal motion, so atoms vibrate around one minimum, and they go by the simplest path, that is around the saddle point, to the another minimum where the products reside. It's again and they go by certain trajectories around this minimum. But if energy is enough, they can go over the saddle point. So this concept of potential energy surface is important. What usually you depict in chemistry is a cross-section of such a surface. That is, you probably have seen pictures that looked like this. Here there is the action coordinates, which is essentially some path going from the minimum over the saddle point to here, and the saddle point looks like a maximum on this cross section, or this section of this potential energy surface. So you probably have heard this. Here we have reactants, and here we have products. There is a question: how to calculate, how to obtain the potential energy surface? There are two basic options how to do it. The first one is quantum chemistry. These methods are based on the Schrödinger equation. There are several approximations to this equation. I will not speak about details, it's beyond the scope of this course. And the second approach is to use a suitable formula. This is called a force field. Better said, a force field is an expression for the potential energy as a sum of many terms. I will speak about these terms in details. Each term has a certain functional form and a set of parameters for different groups, atoms, and so on. Term force field is often used in chemistry. Sometimes a term which is used is just a potential, as a shortcut for potential energy surface, or simply a model. But also we can use a combination. For a part of a molecule, for example an active site of an enzyme, to use quantum chemistry, and force field for the rest. This approach is called quantum mechanics, molecular mechanics. So I will assume that we can calculate the potential energy surface. It also means that we are at the level of the Born-Oppenheimer approximation. That is, electrons are treated in some indirect way, and at this moment we don't see them. That is, we have the potential, and we can use it in many ways. We can use, in principle, a classical mechanics. Then we can use static calculations, for example, to calculate the minimum of energy. It may be useful, such a minimum of energy. This process of obtaining the minimum is sometimes called optimization of a molecule, especially with respect of quantum mechanics. We can also calculate a potential around a molecule, for example, the electric field and so on. But it is more interesting to use this potential energy surface to calculate time development of a system. This is called molecular dynamics. It is called molecular dynamics, whatever is the source, but it is quite typical that if you say only molecular dynamics, usually force field approach is assumed. And if we wish to emphasize that we are using quantum chemistry based potential energy surface, then we call the simulation ab initio molecular dynamics. It is very demanding because calculating a force field is much faster. But we know that our world is quantum, and especially for hydrogens, we often need to consider quantum delocalization of these hydrogens, simply nuclear quantum effects. Then we should use some tricks, some procedures how to include these quantum mechanical effects of nuclei to our simulation. We can use the so-called path integral methods. This is a method that we simulate a certain extended system in such a way that quantum effects are taken into account. Again, I will not speak about details of this approach in this course. We can have both path integral Monte Carlo, we'll see later what's Monte Carlo, and path integral molecular dynamics. Usually this is done with a force field because a combination of both is extremely demanding. Such a quantum simulation is demanding, even with a force field, and combination would be extremely demanding. But we can also use classical mechanics and then add certain quantum corrections that take into account some nuclear quantum effects, the most important ones, especially if we are quite close to the classical world. It's only a small correction. I should here again emphasize the role of quantum mechanics in both parts of modeling. So we can use quantum calculations to calculate the potential energy surface. So here we solve the electron problem. And also, or independently, we can use quantum mechanics to nuclei. And there are, as you can see, 4 possible combinations. The cheapest one is to use a classical force field and classical mechanics, so that, for example, classical molecular dynamics. The most demanding would be both parts at a level of quantum calculations. Sometimes a combination of a force field and classical mechanics in this or that way is called molecular mechanics. That's why here there's an abbreviation of MM, meaning molecular mechanics. Strictly speaking, this includes just using a force field and certain calculations about it. Sometimes it means that molecular dynamics is included, and strictly speaking, it does not include simulation, just an approach using classical mechanics for molecules. So let's start with the simplest approach, which is molecular mechanics and just static calculations. This is molecular mechanics in the strict meaning. It means that we are using the potential energy surface, usually described in the fastest way by a force field. We can do energy minimization, which is equivalent to setting temperature to 0. The 0 temperature molecule is energetically minimized, and this is in a strict way called molecular mechanics, or also structure optimization based on a force field. I've already mentioned that this may be interesting sometimes, but not too much. But if we have such a mechanical model that is a force field, we can use it for a number of other calculations. One of them is the so-called refinement. You have heard that we can obtain a structure of matter from diffraction data. We put our sample, it may be a crystal or sometimes a liquid, into a source of radiation, for example, X-ray radiation, monochromatic X-ray radiation, or neutron radiation, or sometimes also electrons, and we'll get a diffraction pattern. From this diffraction pattern, so-called structure factor, we can calculate the structure of our molecules. But especially if our molecules are large and it's difficult to make crystals of, for example, proteins or peptides, such a structure is imprecise. So we refine this structure using known bond length and in general using a known approximate, of course, force field. And then we'll get a more accurate structure. This is called refinement. Molecular mechanics is sometimes used in biochemistry. Of course, molecular dynamics is better, but sometimes just the molecular shape is good enough to describe what we want to know. For example, there is a model called lock and key for binding a ligand to a receptor. Here there is a receptor. You can imagine a receptor like a protein with, let us say, a hole, but not only a hole, but some hole with, let us say, hydrophobic or hydrophilic parts of it. And we have a ligand, something that goes into it and binds to it, something like that can bind here, and it binds according to the shape. That's why we call it lock and key, and also that hydrophobic, hydrophilic or interaction in some way parts. These interactions can be quantified using a force field, and we can estimate, at least roughly, whether such a ligand can bind to protein. For a better description, we need simulations, of course. At a similar level, there is an approach called Qsar. It's an abbreviation of quantitative structure activity relationship. This is used, for example, in drug design. There are millions of different substances that can work in our body to cure a disease or to affect our metabolism, and it's very difficult to find a good one that would be usable as a drug. That is, we need a method that allow us for fast scanning of these millions of possible drugs, millions of substances. The Qsar method works in such a way that we take a set of substances for which this action in our bodies has been determined and assign certain descriptors to these substances. These descriptors can be many properties, for example, hydrophilicity or hydrophobicity, electric dipole, but also some descriptors that can be derived from a force field or from a force field of a molecule at energy minimum. For example, an area of hydrophilic and hydrophobic parts, and so on. And then we fit the experimentally obtained action of these drugs to these descriptors, and we'll get a model, and then we can scan many other drugs using this model, and we can guess which new substances could work, which cannot work, and so on, at least the first approximate scan. So this is molecular mechanics. But what about motion? Motion, it means that we continue with simulations. And we have, as I have said already, the first method, molecular dynamics. Once again, molecular dynamics is based on time development of a system which is composed of many molecules. To do this, we need to calculate forces acting on atoms at every point and integrate these equations of motion. Again, details will be given later during this course. But instead of molecular dynamics, we can use another type of methods which give the same results. They do not use the concept of time and time development, but still they use a concept of creating one configuration from a previous one. In such methods, we generate a sequence of configurations of the system, and we generate them using random numbers, random moves, and certain rules how to accept or reject these moves. That is, we make an attempt to move a molecule in a certain way, and then this so-called trial move is either accepted or rejected. And the rules how to accept or reject are devised so that we'll get the same probability distribution as in the case of molecular dynamics. This method is called Monte Carlo because it uses random numbers, and you know that there is a casino in Monte Carlo. So there is a third type of method which is called also Monte Carlo, but in this case Kinetic Monte Carlo. Here this Monte Carlo is more precisely called Metropolis method, and there are many variants of this method. I'll speak about it later. The Kinetic Monte Carlo is based on a bit different approach. We have a certain process. You can imagine, for example, growing crystal, or catalysis, that is, there are reactants coming to a catalytic site and doing something there. And we have pre-calculated or measured or whatever certain elementary events. It may be an adsorption of an atom to this growing crystal or something like that. One elementary event. And we have many possible events that can happen at any time. But we also have or know calculated in advance probabilities of this or that event. For example, it may be the adsorption of an atom may be more favorable at some place and less favorable in another place, and so on. And then we'll choose the next event which is going to happen according to the known probabilities. So we must choose it according to certain table of known probabilities. And we repeat this many times, and in this case we'll get the time development of the system. So we can see that these are plus minus 3 possible approaches which are often used. And I should add that we have also quantum simulations. I will not cover them in this course. And perhaps you know that there are casinos also in other cities than Monte Carlo, for example in Las Vegas. And we have also so-called Las Vegas algorithms, which is a different type. Such algorithms also use random numbers, but they give deterministic results. The random numbers are only for control of the course of calculations. For example, if you are looking for a minimum by a Monte Carlo, or here better said the Las Vegas algorithm, you may go towards the minimum using several paths, but eventually you will end up in one minimum. And this minimum should not depend on the random numbers generated. So such types of algorithms are called Las Vegas algorithms. In Monte Carlo type algorithms, we are using random numbers, and that is, our results are statistically correct. The longer simulation, the more accurate result, but always the result depends on the random numbers we are using. So we have a couple of methods which we can use in chemistry for studying matter, and there's a question: what is interesting to study? All this business started 50 years ago, let us say, even more, by studying simple systems, liquids. I should say here that liquids are in between of gases and solid matter. Gases can be calculated easily analytically, no problem. As regards crystals, it is a bit different than difficult tasks. Of course, there are difficult tasks also for simulations, but sometimes or many times a crystal can be calculated again analytically because it has a perfect structure. In liquids, there is chaos, which is difficult to evaluate, and this is a room for simulations. The first simulation was a simulation of hard disk and then of hard sphere, that is molecules which are spherical and hard. Then something like liquid argon, water, and more difficult systems have been simulated. We are looking for several questions: how structure affects properties. For example, you know that water has many quite strange properties which are different from the properties of other liquids. For example, the density maximum at 4 centigrade and so on. And I can say that a lot about the structure of water and explanation of these anomalies has been obtained by simulations of water. Then we can simulate solutions of salts in water, of other substances. As regards liquids, we can study so-called ionic liquids. Perhaps you've heard about them, it's quite popular too. Then we can study phase equilibria, solubility, and so on. I should say here that at conferences often there are people from the shell company. The shell company pays scientists to study mostly hydrocarbons naturally by simulations. Solubility. Again, solubility is important, for example, in drug design or pharmaceutical design, better said, because if you have a drug that works fine, you must deliver it to our body, that is to make a pill out of it. And solubility in let us say stomach and so on, and also how it crystallizes and so on is important. And again, we need to scan many possible substances, and simulations are one possibility how to do it. We can study surfaces, interfaces, surfactants. Again, it's important in biology. We can study also solids, what we are interested in for solids. Well, the crystal structure is usually known, but what we are interested in often are defects in materials. The defects influence how the material behaves, for example, whether it's malleable, whether it's brittle, and so on. And it can be, or the kinetics of these defects can be simulated by molecular dynamics. These simulations are huge, there may be billions of atoms, but it works. We can study adsorption. Perhaps you have heard about zeolites. They are used as adsorption materials, as catalytic for catalysis and so on. Another great field of simulations is biochemistry. I would say not a field, just a business, because it's very complicated. We can simulate proteins, nucleic acids, and stuff like ion channels, lipid membranes, and also, as I've already said, enzymes, and all this stuff which is important for our understanding of what's going on in living cells. From the other side, we can study nano-objects. We can study them either composed of individual atoms and molecules or by bodies themselves at the coarse-grained level. We can study polymers. The field of polymer simulations is a bit different of what I'm going to cover in this course. Often we use lattices, lattice models, not atomistic models. I will speak in a brief about this. We can study the so-called self-assembly, usually using coarse-grained models. That is how big molecules create or bind together to create higher level structures. But if we have a set of powerful methods how to simulate molecules, we can use similar methods for simulations of many other interesting things around us. We can study granular materials. We can use similar methods for optimization of whatever. For example, it's quite actual now spreading of epidemics. We can study the so-called active matter. Active matter, these are maybe, for example, micelles of nano-objects or whatever, which can move, which has energy or is given energy to move somewhere. It's quite similar to so-called agents. That is, agent-based models use something, or elements of this modeling is something that can react in a complex way, having, let us say, energy to do something or make a decision and so on. Such models are popular in evolutionary developmental biology, where elements of simulations are living creatures, for example, males and females, predators and prey, and so on, and they interact in nature in some way. And we can ask what are the key rules, or better said, we put certain rules there, and we'll ask what is the key principle why this part of nature develops in certain direction. This type of simulation may be based also on individual genes, which bear certain information and are subject to evolution in the spirit of Dawkins' gene theory. And now a few examples about molecular mechanics, microdynamics, and so on. So the first example will be about molecular mechanics, a very simple one. You know that cyclohexane may occur in two different conformations. One is a chair conformation and one is a twisted boat. This chair conformation has a lower energy. Here there is certain experimental value and a model that you will see, which is not exact, but it is qualitatively it is. So I will show you now a very simple code doing molecular mechanics. You've already seen it. Here's the energy. It is kilocalories per mole, so the unit is different. And you can see here that this is the chair conformation. And I will now try to change this conformation. So I'll mark the whole group here and we'll move it in such a way. You can see that it now looks quite ugly. I can calculate energy and it is huge, but doesn't matter. I can proceed by minimization. So after several steps of minimization, we can see the twisted boat conformation here. Of course, it is a simple molecule, and this model is as accurate as the force field, which is inside here. This force field for this is called Charm 22. It is quite old, but good enough for showing to students. So this was an example of molecular mechanics. Here I will show you an example of liquid water. It will be 10,000 molecules simulated at ambient temperature in a periodic boundary conditions in X and Y. I will speak in details about this, which is put on an adhesive pad, and there is a lid on top of it, which you will not see. This simulation looks like this. You can see that once a while a molecule evaporates, and because there is a lid up, it will return back soon. So this movie is about trillion times slowed down and billion times enlarged. Here is a simulation of a droplet of water. In the left you can see it using a ball model, and in the right there are hydrogen bonds depicted. Because in a simulation we know everything about the system, we can calculate according to certain rules hydrogen bonds and study how the system evolves with respect to hydrogen bonds, and study the structure of the hydrogen bond network. Here is a frozen droplet, such a small hail, with a structure of hydrogen bonds again. You can see that we have mostly pentagons here, sometimes hexagons and squares. So this is typical for such hydrogen bond network. This is another movie, but probably it's not a good idea to have it like movie here. You can find it in links that I will put to you to your e-learning. And one example from biochemistry. You may have heard that the holy grail in biochemistry is to predict the structure of protein, the so-called protein folding. How a protein, which comes out of ribosome, is folded to its shape that is active in our bodies. It is very difficult, so we can do it, we can try to do it in the opposite way, to take a protein and break it. And it is why such an experiment. There is an electrospray needle with high voltage, and it is fed with a solution of a protein, in this case Cytochrome C. This solution is sprayed here into small droplets which are charged and wet. These droplets go into this apparatus. They are desolvated, that is dried out, so we have ions of Cytochrome C going further. Here they are focused by magnetic lenses, and we have a beam of such ions going further to a drift tube. It is a tube which is filled with helium at a very low pressure, and there's electric voltage here. What happens is that individual ions of Cytochrome C go through this gas, and it has certain viscosity. So they go by certain speed, and this speed, the drifting velocity, depends on the cross section of this molecule. So essentially here we measure the size, the cross section of Cytochrome C, that is how it is unfolded, and then we determine the charge or ratio of charge and mass. That is, we know the molecule, that is the charge of cytochrome C. So this is the experiment, and there is a question whether a theory, that is simulation, is able to predict similar behavior. So here is a playback of such a simulation of cytochrome C. There is heme here in pink with iron atom inside, and you can see that such a molecule, in this case it is dry with certain charges put on it by certain rules, so that these charges are at surface, and these charges cause the molecule to unfold. Then if we have such unfolded molecule, we can also determine, after it unfolds, we can determine the cross-section and compare it with the experiment, which worked, well, not greatly, but at least qualitatively quite well. That is, the higher charge, the higher cross-section. So we can assume molecules that we have at the end of this apparatus look like this. Another example. I have a computer code which I have written especially for students to show basics of simulations. This code is based on two-dimensional atoms because it's easier to show configurations in 2 dimensions and contain certain type of potential, and we can study how matter behaves, or the simple model behaves with repulsive attractive walls under the forces of gravity, both Monte Carlo Microdynamics and under certain conditions for simulations. And we can study a lot of phenomena. Now I will show you how it works, and what's important for you, you can download this software and try it by yourself, and I will use it during this course a lot to show you principles of simulation, because it's a software done for teaching. In a prepared system we have different possibilities here. We can choose gas in box, which is actually what was in the beginning here, and I can now slowly cool the system down to decrease temperature. You can see that on a decreasing temperature I get a droplet. This droplet is liquid. It's a two-dimensional liquid. You can imagine, for example, surfactants on a surface of water if you wish, but it's qualitatively the same as in 3 dimensions. If I cool down more, I get a crystal. If I shoot, it's hexagonal here, and there is no trick about it here. It's this hexagonal crystal is created spontaneously just because of intermolecular interaction of the force field. Diffusion. Here I have 2 types of molecules. Actually they are the same, just colored different way. So we can see how diffusion is a relatively slow process. Gravity. I'll use this simulation later to exemplify the so-called barometric formula, or Boltzmann probability. Vapor-liquid equilibrium. It will be your task at the end of this course to perform simulation with this model and to verify the Clausius-Clapeyron equation. We can study nucleation. You are nano and micro technology, so you certainly know what's nucleation. You can create nanoparticles out of it. We can study capillary action. Here we have 2 types of walls. Green ones are attractive and red ones are repulsive. So you can see here a meniscus that is capillary action is positive. We have a, let us say, hydrophilic surface and water in it. But because I'm performing simulations, I can simply change the walls into repulsive, and we have the opposite effect. We can study crystals. This is the hexagonal crystal. We can put defects in it. This is the edge defect, which eventually goes to the border of the crystal and disappears. Vacancy, it diffuses through the system but relatively slowly. So you can try it by yourself, but I'm not patient enough now. Or interstitial atom, which actually is difficult. I'll try it again. Still it fails because the energy is too high. We got vacancy. Never mind. Another example, so-called self-assembly. It is a part of the so-called supramolecular chemistry. That is assembling of higher structures from small molecules using non-covalent forces, maybe hydrogen bonds typically, or van der Waals forces only. In this simple example, I first show bivalent particles in a solution. They are sometimes called Janus particles according to a god called Janus. So the simulation, it is performed while decreasing temperature, and when temperature decreases, the particles become bound together and make such filaments which go through the box. It's a periodic box. And if I add some tetravalent particles, we can see that the system will look differently. This is a very simple example, and the structures obtained are irregular. But sometimes we can use irregular structures like here. An important procedure in many branches of science and technology is minimization. Minimization of a certain complex function of many variables. As an example, I have chosen a cluster of sodium chloride. You know that if I take liquid of sodium chloride and will cool it down sufficiently, you will get crystals of rock salt. Here I have a cluster. So it looks like quite small, so I will use already known code for molecular mechanics, and I will randomly shuffle the atoms and let the program minimize it. You can see that I'm getting certain conformations. We can watch the energy. I will minimize, and sometimes they are quite strange. Often there are motifs of some cubes here, so it's close to the rock salt structure, but likely this is not the absolute minimum. That's because the minimization using this algorithm, the so-called greedy algorithm, goes directly to the nearest local minimum. Very likely we will not get a global minimum here. To get a global minimum, which is what we are mostly interested in, we need to do something more sophisticated. From these more sophisticated methods, the simplest one probably is the so-called simulated annealing. Essentially, it is simulation with decreasing temperature. There may be several recipes how to decrease the temperature. We may try decrease, increase in ways and so on, but these are technical details. Essentially, here I will show this again. I started with something random, and in the end I obtained something that is very close to ideal crystal. It is elongated, but still it has cubic structure. This is called simulated annealing. The first method of fast cooling is called quenching, or sometimes greedy algorithm principle, or in minimization generally these algorithms are called greedy, which go to the nearest minimum. Okay, this is a simple chemical example, but we often need to minimize many things in, for example, economy and so on, in logistics. You can imagine a factory producing something, and there is a product on which several processes are performed, like to put two screws, to paint it, and so on, and it goes through a line, and there are perhaps several lines, and there may be some delivery of subparts, components, and so on, and we need to essentially maximize our profit. A school example of such optimization problem is a so-called traveling salesman problem. It is a man that needs to go through certain number of cities, let us say 100 cities, to visit every city once, or at least once, and for simplicity to go back to the original city. And the cost of this travel, let us say the length of this travel, should be as short as possible. So this is called the traveling salesman problem. It is a difficult problem to obtain the true minimum. The number of operations grows exponentially with the number of cities. But often we need something which is pretty good. We don't need the absolute minimum, but something that is pretty good. So how to do it? Let's start with 100 of cities which are put randomly in a square, something like this. And let's start with a random path. Just we take all these cities in a random sequence. Then we'll do several steps of simulation, or many steps of simulation. The basic simulation step will be change of two randomly chosen cities. I choose two cities randomly and change the path. And now I will look what the new path is about its length. Is it shorter? And I have two options. In the first, the so-called greedy option, the new path, the shorter path, will be always accepted. In a more sophisticated Metropolis Monte Carlo simulation, it will be accepted only sometimes. But during time, I will decrease the parameter of this expectance, the so-called temperature, and will have a bigger and bigger tendency to accept lower or shorter paths. At the beginning, I will be able to scan also quite long paths. And I will show you now such a simulation. Now the computer is creating the simulation. I always start with random numbers, and this is the greedy algorithm. Actually, with 100 cities, one step of the algorithm starts from the beginning. This is a random path. One step of algorithm is just swapping two cities. Here, one step is many such steps. But you can see if I continue, that the configuration changes. It improves. I will go it faster, and apparently, in the end, the path is shorter than in the beginning. And now the Monte Carlo algorithm, that is simulated annealing. It allows at certain points during the simulation for increasing the path, and it allows me to go to something that is closer to the global minimum. Also, there is a genetic algorithm possible. I will speak about it quite briefly later. It's not the mainstream of this talk, just that you know what's hot topic today, or it's been hot topic for 20 years, let us say, but it's still very useful. So now the genetic algorithm, and now I will compare all three solutions. This is a solution from the greedy algorithm. Here in the line you can see the length obtained. Simulated annealing is better, and the genetic algorithm a bit worse but better than the greedy algorithm. If you are interested in the results, you can see them here. These are the lengths for this simulation. Actually here the genetic algorithm didn't work quite well. It depends on random factors, of course. So I can use methods of simulation for optimization. The simplest algorithm like this is called simulated annealing, and essentially it's a simulation of different type, Monte Carlo or Microdynamics, with decreasing temperature, also with certain temperature changing protocol. The genetic algorithms are based on the principles of evolution. We have a certain function to minimize or maximize. Here usually we maximize, it's just a matter of sign. And this function is called fitness. It's the fitness of an organism, whether it will survive. A configuration, we use term configuration for molecules. Here we can call it an individual, an organism, or perhaps its genome, which is essentially in biology a chromosome. And a chromosome is a list of alleles, that is like a list of certain properties of this organism that affect its fitness. For us, it is a column of numbers. We start with a certain population. That is, unlike for simulated annealing, where we have at the moment one organism, one configuration, we have here a set of let us say chromosomes or individuals, like here. These individuals have certain fitness. So these are numbers calculated from these configurations. Let us say the length of the path of a traveling salesman, or the energy of a protein, or something like that, and I create a next generation, and I do it in a similar way how the nature does. First, I will kill the least fit individuals that are worth. Simply, I will kill them. Perhaps a better use a rat to kill them. Then I will copy this to create more individuals like this. Let us say the same. And I can make certain mutations here. That is, at certain points I will change the chromosome to something else. And then the most important step comes. This is breeding. I take two parents. Usually we don't distinguish in these genetic algorithms males and females. We take two individuals, let I say this one and this one, and I exchange parts of the chromosome. For example, like exchange these two. There are several details how to do it, whether it is full random or some protocol of it. So I'll get a new generation, which is formed of the better half of the previous generation with certain modification, and I repeat the process. In this process, I will keep several alleles of it, several possibilities of what can be good or bad, and combine them again and again. In my population, I can have worse and better solutions, and they keep combining until I get something that I'm happy with. If we there is a problem which is a bit of technical. Here I can have real numbers. It is not good to cut a series of bits of a real number into half, so usually we are using special coding of real numbers. And such genetic algorithms are useful in optimization in logistics, in economy. Generally, control of processes is example of the traveling salesman problem. They are used in biochemistry for solving the protein folding problem, for circuit design or antenna shapes, quite interesting design, and also algorithm design. Quite interesting procedure which is very useful. And again, I should note that here you can see such a plus. It means that it's something added and it's a main stream of this talk, and no details will be part of the exam, of course. We are coming to something that is now very popular. These are neural networks or deep learning and so on. This is a procedure that takes certain input, whatever it is. It may be a picture of something we need to recognize, or elements of speech or text or something else, and these inputs are expressed as numbers or symbols. They go to several so-called hidden layers, and they are combined here. They may be combined by many procedures inside. If these are real numbers, you can imagine, for example, a sum of inputs, and it goes through a certain function, for example, such as save function, which then gives the output. And the output goes to another layer, and then to the final output. This is a very general scheme, but to give good results, we must train this network. So we take a lot of inputs for which we know the outputs. For example, a lot of pictures of cats, then we know that there is cat there. And there is now the most important part. This is training of this neural network. Training means that I am finding, mixing parameters, and perhaps the full functions here, it depends on details, of these hidden layers until the output says me it's a cat. And for other pictures, it's a dog, or it's a mouse, or whatever. So this is in general an optimization problem which can be solved by a method of genetic programming or simulated annealing or some other method that is finding many parameters. That it is typical for these neural networks, unlike standard procedures like least square method, that we have many more parameters that is necessary. Okay, so this is detour to some more optimization, and now let's continue with examples of simulations. Perhaps you have mentioned that if you have a stream of water coming out of a tap, it breaks after some time into droplets. That's because this stream becomes unstable if it is thin enough. There is certain theory about this that can be calculated, but it's not important now for us. The theory says that the maximum instability is for so-called wave number, that is number of or this length essentially 2 pi over this length. It is the wave number times the radius is logarithm of 2, but we can also simulate this, and I will show now this simulation. It is something like liquid argon. You can see that the stream really split into 5 droplets, and this number of 5 is approximately the same as predicted by this theory. Another example, again in this case from our laboratory. There are experiments with water vapor that is put into a certain vessel where it is at elevated temperature and pressure, and it expands through a small nozzle to a vacuum. During this expansion it creates such a jet, and this expansion is adiabatic, and such high temperature vapor cools down and nucleates. So what you get here are small droplets or clusters of water. These clusters are interesting from the chemical point of view. We can irradiate them by lasers, put pollutants on them, and to study reactions occurring there. But there is a bit problem that there is a disagreement of the size and shape of these clusters with theory. So that's why we tried a simulation of this process, a direct simulation of expansion of gas into high volume. It's called supersonic expansion because the speed of this jet is higher than the speed of sound. So again, I will show you the simulation. Now here we have gas, vapor, and if the box grows, clusters appear. And the question is, in this case there are 2 clusters and perhaps a few very small ones, and the question is whether this is an agreement with the experiment, and there are in current state of the art some problems with this. Another example of a simulation, you should be interested in it because it deals with nanoparticles, and you know that the melting point of nanoparticles is lower than the bulk substance. So example 1, let's take a hail of 600 water molecules, such a cluster with a crystal structure, and let's heat it gradually. So you can see here on this simulation, red are oxygens, white are hydrogens, and green are hydrogen bonds. And the number that you see in this corner corresponds to the number that is here. So now we are coming about here. So still we have a crystal which is heated up, and now we are in the process of melting the nanoparticle, so that the heating rate decreases. Or better said, the heating rate is the same as the heat added to the system, but the rate in which the system increases temperature has a plateau here. So this is an indication of melting, and it occurs at a lower temperature than in the bulk for this model of water, which actually has a lower melting point, but qualitatively this works fine. And a similar simulation for gold, yeah, it should come soon. This is a crystal of gold, and again here it starts to melt, and it's melted. Again, the melting point is smaller than in the bulk gold. Here is one example of a coarse grain simulation courtesy of Robert Waha. So I will show you it. It is a simulation of a virus going to membrane, and eventually it will be covered by the membrane and will go through. You can see that it's quite a complex simulation. A virus is quite big stuff. There's another simulation releasing of RNA from such a virus. It is a different type of virus than COVID. And it is a coarse grain simulation that is DNA or RNA. I don't remember what is it. Here is modeled just by beads. Okay. It was in water, but water wasn't shown because you wouldn't see anything. Electrospinning. It is popular in laboratories, so you should be interested in. But this is a very simple simulation done by some people from UC nad Labem, but not with a polymer or a solution of polymer, but only with water. It's quite a high electric field, a very decent simulation time. Perhaps you have heard about the Taylor cone. That is how electrospinning starts because of the high voltage put into the electrodes, and start with Taylor cone, and the tip elongates and produces a jet that is then stabilized. So let's see the simulation. So you can see that tips are starting here. Sometimes a molecule evaporates, but it's not important for the process. And the Taylor cone, and these tips gradually are drawn along the electric field lines. You can also mention, if you look well, that here hydrogens are in the right hand side and here oxygens are in the left hand side. That's because these molecules in this high field are really oriented along these lines. So this was a simulation of electrospraying using a very simple system. And this is the end of the introduction, and the next talk will be with some mathematics and some theory, but I hope you will enjoy it.